All right, let's dive in. Today we're tackling AI learning, and a question that I'm sure a lot of you are wondering about. Can AI actually, generalize?
It's a really big question. It gets at whether AI can do more than just, copy patterns from data.
Hmm.
Can it actually understand and solve problems in new situations? Be
Yeah.
flexible, adaptable.
Right. And we're going to figure this out using some new research on two training techniques,
Hmm.
supervised fine-tuning, or SFT, and reinforcement learning, or RL.
Yeah,
We want to know which one is better at applying what it's learned to totally new situations.
absolutely.
Now, we're going deep into an academic paper today, but I've got an expert here to guide us. So before we get lost in the research, let's break down SFT and RL. What's the core difference? What are we even talking about here?
Well, there are like two different philosophies of learning. Imagine we're teaching someone chess,
Right,
right?
right. Yeah.
With SFT, would show them tons of examples of board positions and the best moves for each. So they're basically learning by memorizing a huge library of correct answers.
So SFT is like following the expert's lead, just replicating those successful patterns.
Got it. But RL, how's that different?
With RL, you give them the rules of the game and you let them play. You give feedback, good for good moves, bad for bad moves, and they figure out winning strategies through their own, trial and error.
Ah, so it's learning by figuring things out on your own. You're
Exactly.
getting feedback along the way. That's super interesting. So this research didn't use chess though, right?
Right.
Tell me about those two environments they used, general points and VIRL.
Okay, so general points, think of it like a supercharged version of that card game 24.
Oh yeah, I know that one.
Yeah, so the AI has to figure out how to combine four numbers using, math to reach a target number. They have a text-based version, GPL, and a visual one, GPVL, where it has to recognize the numbers from images of cards.
So it's testing their logic and visual perception.
Yeah.
That's pretty clever. What about VIRL? What's the challenge there?
VIRL, it's like a step up. Imagine we drop an AI into a realistic simulated city.
Whoa, okay. And it has to follow instructions to get to different places, relying on either text descriptions, VRLL, or actual street view images, VIRL-VL. So basically, it's a test of spatial reasoning and visual navigation. Like, how well can it get around in a space?
Like a self-driving car, but navigating human environments.
Exactly.
That's really cool. Now, I know you mentioned this idea of out-of-distribution testing, and that's key to understanding generalization, right?
Right.
Can you explain that a bit more?
Sure. So in distribution testing is like evaluating the AI on stuff similar to what it was trained on.
Okay.
But out of distribution testing, that's where it gets interesting. It's like throwing curve balls at the AI, presenting scenarios it's never seen before to see if it can truly adapt.
Oh, I see. So how do they create those out-of-distribution challenges?
Well, they got creative. In general points, they introduced new rules for how certain cards are valued.
Like what?
So a king might be worth 10 during training, but then suddenly it's worth 13 during testing. Forces the AI to adapt its understanding beyond just memorizing specific answers.
Makes them think on their feet. And in VIRL, how did they make things challenging there?
They did something really clever with the navigation instructions. Let's say the AI is trained using cardinal directions north-south,
Okay, yeah.
but then during testing, the instructions switch to relative directions, turn left, slightly right. The AI can't just follow a memorized route anymore.
Right.
It has to understand spatial relationships and adapt its movements based on where it is.
It's like the difference between reading a map and actually understanding the city, right?
Yeah, exactly.
And I bet they've probably messed with the visuals too,
Yeah.
right? Especially in VIRL, where the AI is using those visuals to navigate.
Oh, for sure. Imagine training the AI to navigate in sunny daytime conditions in, say, New York City, and then testing it on a rainy night in London. Or even just changing the angle of a street view image a little bit during testing.
Wow.
Forces the AI to rely on a deeper understanding of visual cues and not just matching pixel patterns.
So they really made it tough. Okay, with all these tests, which method came out on top? SFT or RL? Who's the generalization champ?
Wow. Reinforcement learning. It was the clear winner when it came to generalization.
Wow, RL really took the crown. I have to admit, a part of me was kind of rooting for SFT, like the underdog.
Yeah.
But hearing about all those crazy out-of-distribution tests, it makes sense that RL would be better at handling those curveballs.
Yeah, it shows how powerful learning by trial and error can be. The RL agents, they built a stronger understanding. They could handle those surprises that tripped up the SF2 models.
Okay, but give me the specifics. What are some examples that show just how much better RL was at generalizing?
Let's talk about general points first. Remember how they changed the card values during testing?
Yeah,
Well, the RL models adapted to those new rules, like JAMPs. They scored up to 11% higher than the SFT models in terms of accuracy.
11%. That's not just a little bit better. That's a huge difference. What about VRL? Did RL still have the edge in those more like visually complex environments?
It did. And in some ways, the results in VIRL were even more impressive
Really?
because you've got all those layers, spatial reasoning, visual processing, following instructions. And they found this consistent pattern. Whenever there was an out of distribution challenge, like navigating a new city or changes in lighting, the RL agents just did so much better than the ones trained with SFT.
Yeah, that makes sense. Navigating a new city, that's the ultimate test of generalization, right? You can't just rely on memorized routes.
Right, exactly. It's about understanding, like, how space works, not just memorizing paths. But get this, one of the most surprising things they found was that RL didn't just improve generalization, it also made the agents better at visual recognition.
Wait, hold on. You're saying that learning to navigate a virtual city made the AI better at seeing?
Yeah.
That's crazy. How does that even happen?
It was a total surprise. They were focused on generalization and navigation, but then they saw this big improvement in how well the RL agents could process and understand visual information. It's like those challenging environments forced them to develop better visual skills.
So it wasn't even something they were directly aiming for. It was like a side effect.
Exactly.
That's mind-blowing. And what does that mean for AI?
Yeah.
If RL can boost visual perception just by, like, accident, what other abilities could it unlock?
That's a huge question.
Right.
It suggests that RL might be the key to AI that doesn't just make decisions, but actually understands the visual world like we do. Like, imagine self-driving cars that truly see, robots that can do complex stuff in messy environments.
This is getting me so excited about the future of AI.
Okay.
But, okay, let's not get ahead of ourselves. We can't forget about SFT entirely, can we? You mentioned it still plays a role, even if it's not the generalization superstar.
You're right, it still has its place, especially at the beginning of training. They found that using SFT first, just to kind of stabilize the model's output, can actually make it easier for RL to take over and refine things further.
So it's not an either situation, it's more like a team effort.
Yeah, exactly.
SFT lays the groundwork, and then RL takes it to the next level. That's a pretty cool partnership. Now, you also mentioned something called verification iterations. How did those fit into all of this?
Oh, right. So verification iterations, they're like extra steps where the AI gets multiple chances to get things right.
Okay.
Instead of just evaluating one action, it can try different things, get feedback at each step, and adjust its strategy.
It's like having a coach, right? Guiding you, giving you hints along the way.
Yeah.
And did they find that these verification steps actually made a difference?
Oh, yeah, absolutely. They saw that more verification iterations led to better generalization, especially with the RL models. It was like those extra chances to try things out, learn from mistakes that help them develop a deeper understanding and become more flexible.
It makes sense. It's not just about giving the AI a chance to succeed, but also a chance to fail and learn from those failures. Okay, so we've been focusing on these specific environments, general points, VIRL, but what do these findings really tell us about AI in general? Can we apply this to real-world stuff?
Well,
Yeah.
it's the big question, right? Like, can we take what we've learned from these, simulated games and virtual cities and actually apply it to the real world?
Yeah, that's what I'm wondering. Can we?
Well, we can't just like copy and paste these results into real world situations, but the important thing is the idea behind it, RL's ability to help AI learn in a deeper, more adaptable way.
Okay, so even though these experiments were in, like these controlled environments, the way RL helped the AI generalize suggests it could be really powerful for real-world problems.
Exactly. Think about robotics, healthcare, even personalized education. These are areas where AI needs to be able to handle things it's never seen before, learn from experience, get better over time.
So instead of trying to program AI with, like, every possible answer,
Yeah.
we can use RL to give it the tools to learn on its own, right?
That's the idea. It lets us go beyond just rule-based systems. It lets us create AI that can actually learn and evolve. But, we've been talking a lot about how great RL is, but we have to remember that every tool has like limitations, right? Things to be careful about.
Yeah, good point. What are some of the challenges or limitations of RL we need to keep in mind?
Well, one big one is designing the reward system. In these simple environments, it's easy to define rewards. You reach the target number, you get to the right place. But in the real world, it's way more complicated.
Right, because it's not like a game with a clear objective. The real world is messy.
Exactly. So we have to figure out how to create rewards that actually match the outcomes we want. If we get that wrong, we could end up with AI that's doing the wrong things, things we didn't intend.
Well, that's kind of scary, honestly. It's a reminder that we have to be really careful and responsible when we're using RL, make sure it's aligned with our values and ethics.
Absolutely. And another thing is the computational cost. Training these agents can take a lot of computing power, especially as the tasks get more complex.
Right, so it's not just about the algorithms, it's about having the computers that can actually handle them, especially for those big, ambitious, real-world applications.
Yeah, that's a real challenge. But even with these challenges, the potential benefits are just too big to ignore. Imagine AI that can help doctors diagnose diseases, personalize education for every student, or even find solutions to climate change.
It's like AI becomes a partner in solving problems, helping us tackle these huge challenges.
That's what's driving this research. That's why people are so excited about RL.
This has been an amazing deep dive. We started with this simple question, can AI generalize? And we ended up exploring this whole world of research, these surprising findings, and really thought-provoking questions about what AI could become.
Yeah, it's incredible to think about. We're just scratching the surface of what AI can do.
I know. I'm feeling so inspired right now. So to everyone listening, we want to leave you with something to think about. If RL can unlock these hidden talents in AI, what other breakthroughs are waiting for us? Keep exploring, keep asking questions, and keep pushing the boundaries of what's possible with AI. Until next time, happy learning.